Did you see any similarity between those triangles? The bigger and the smaller? Of course, they have similar shape. You may wonder, why are they so similar or similar in shape? One of those reasons is that their sides are parallel in pairs, We name this side as the side that corresponds to this side, and this to this side, and this side to this side are the corresponding sides. 3 pairs of corresponding sides. 1 pair, 2nd pair, 3rd pair. And you also see 3 pairs of corresponding angles. And they are equal in size. I say that they are equal, but I mean equal in measure or size. What of these properties guarantees similarity? I'm going to show you that parallelism of the sides guarantee similarity. Otherwise, equality by pairs of corresponding angles also guarantees similarity. You may recognize similarity even if you move one of the triangles. They keep the sides parallel by pairs, and you see also the angles equal by pairs are equal. I mean, this pair is equal, this pair is equal in size, and this pair is equal in size. Moving one of the triangles, you can see the quality of the angles. See that? And more than that, see this? If you put this angle over its corresponding angle, I mean this angle in the bigger triangle, using the same vertex as the smaller triangle, you see those 2 angles don't seem to be just one, but they are 2. One for the smaller and one for the bigger. It's the same. So, and see the parallelisms here. And more than that, these sides, when you move the triangles, they fit, at least in direction, but not in measure. But notice something about the measure of these triangles. Notice something. There is an special relation between the measures of the sides of similar triangles. See that? AC divided by A prime, B prime, I mean this and this, is equal to 15 divided by 7.5, which is 2. So those are corresponding sides for those similar triangles. And check now the relation between this and this. I mean, one of the sides of the bigger one, AB divided by A prime B, gives us 22 divided by 11. Notice that. Now go to another pair of corresponding sides, like this, and the whole side of the bigger triangle. I put those lines, trying to compare measures. Okay, But to compare them, I have to put both vertical. Oh, I'm sorry. It changed the size. I'm so sorry. It's very difficult to move this without changing the size, you know? Since I don't have the ruler still working, I cannot measure this. But we can measure the diagonals of the small squares here. I mean, how many squares are small? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. 22 is BC. But 22, I mean, since those are the squares, if I measure with this, it's an horizontal measure, like this one, but I measure it in the diagonal of the small square, it measures more, but let's count the number of those diagonals or those small squares and see that we have here 1, 2, 3, 4, more or less 20, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. I'm not so sure, you know. But it is a different kind of measure. BC divided by B prime. And I say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Let's suppose it is 22. And then these one are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's not exactly because I cannot measure, okay, maybe it's 11, you know. But anyway, having a ruler, I could check this easily, but the ruler is not still installed, you know. What I mean is that the relationship between similar or corresponding sides is just the same. I don't mean that it is always 2. It depends on the size of any triangle, of the bigger and the smaller. But in this case, it's 2, the relation between one side and the corresponding, and then other side and the corresponding, another side and the corresponding. I did the division this way, 15 between 7.5, 22 between 11, and 22 divided by 11, more or less. This relation between the sides of similar triangles is not always the same, because it depends on the size, the relative size of this triangle and the other triangle, you know, the relative size. Being the other bigger than the smaller, the relation grows, you know. But in this case, it's about 2. You have checked. more or less, because it's not math, but painting. Now, what happens if instead of dividing one side by the corresponding in some order, by pairs, we divide sides of the same triangle? See those sides that form, in this case, the 90 degrees angle, the right angle. Divide the side AC of the ABC triangle between the side AB of the same triangle. Then you have 15 divided by 22. 15 divided by 22. See the answer. Is 15 divided by 22. There is no simplification, you know. But now instead of dividing those pairs of the same triangle, or those sides of the same triangle, divide the corresponding side of the similar smaller triangle. 7.5 instead of 15, and 11 instead of 22. See that? The same number? You don't need to know the number, which is this number. But notice that dividing and the corresponding sides of the smaller triangle, 7.5 between 11, we got the same relationship. Let me illustrate once more that there is a proportional relation between sides of similar triangles. See this case, see this triangle, you know? I'm gonna fit it to the axis. There it is. And there is no doubt that this triangle is similar to the bigger one over here. Same angles. This angle is equal for both the smaller and the bigger. And this angle is equal to this, and this is equal to that. They are similar. Okay, let's see what is the relation between sides of those triangles. Use relation in the same triangle. Divide this length by this one. See, this length is, you know, this length over here is 1, 2, 3, 4. This length over here is 4 also. Okay. This length over here follows the Pythagorean Theorem. And it is the square root of the squares of the size of the right triangle. The sum, you know, which is gonna give you 32. But you have to take the square root. This is the square root of 32. I have the measures of the smaller triangle, you know. Let's see the measures of the bigger triangle. This measure is 8, actually. And this measure is also 8. And now, this measure over here has to follow also the Pythagorean Theorem, which gives you the square root of 64 plus 64, which are the squares of the size of the right angle, square root 128. More than that, we better simplify this. 32 is equal to 16 times 2. Then you can start from here. The square root of 16, which is 4, times, this cannot be extracted from the root. This is a more simple way to express this length. And now, this 128 is 64 times 2, Then you can extract here the square root of 64, which is an 8, and the 2 keeps inside of the square root, and you got here a simple expression. You have all the measures here. If you divide this between this, you get 4 square root of 2 divided by 4, and then you get square root of 2. Do the division of the corresponding sides of the bigger triangle. Divide now this side, a square root of 2, instead of this, between this side instead of this. What you actually did, you know? And it gives you this number here divided by this side, then, which is 8, and you again obtain the square root of 2. It means that dividing two sides from the smaller similar triangle, you get a number, and divided the corresponding sides in the bigger similar triangle, you get the same number. So those divisions are equal. There is a proportionality between sides. See, for example, that if you divide, instead of that, you divide those sides in the smaller, you get a 1. And if you divide those sides in the bigger, you also get a 1, you know, the same proportion. It means that if you have two similar triangles, like this and that, you don't require to have a right angle, like here. But anyway, A, B, C, and A prime, B prime, C prime. If you divide AC between AB, you don't know the number, but be sure that it is equal to A prime C prime divided by A prime B prime. The relation between two sides of similar triangles by division is the same number. Suppose that this is twice this, then this should be twice this. Suppose that those are equal. Those are smaller, but they should be equal, you know, in the same relationship. Let me illustrate it using Google. This picture shows the proportionality between sides of different similar triangles, dividing this by its corresponding side in the other triangle gives one constant. It is same as divided this by that, the same constant, and it's the same as dividing this by this, the same constant. Then it is called the constant of proportionality. It means roughly that these sides are 1.74 times the size of the other in measure. This other challenge you to find the other sides of the second similar triangle, knowing or finding the constant of proportionability. How could you find it? Either dividing this between this, or in this case I prefer divide the other way. 24 divided by 8 is 3. Means this one is 3 times the other, So this should be 3 times this one. Then you got here the 18, and you may measure this and multiply it by 3, because they didn't give you the length, But anyway, this one gives us the opportunity to check the similarity using the relationships between size in many ways. For example, 12 divided by 6 is 2, 18 divided by 9 is 2, 16 divided by 8 is 2. The constant of proportionability is 2. Those lengths are twice those lengths, but it is also true that if you divide those both, you won't find the reason of proportionality between triangles, but you get a very important result also. If you divide 18 between 12, which is the proportion between those two sides, it should be equal to the proportion between those two sides, which will be 9 divided by 6, which is true. The relation between those sides is, let's simplify, 3 divided by 2, 1.5. This side is 1.5 the other. So this side over here should be 1.5 the other, which is true. Remember, if they are similar, they keep the proportions. You can check the proportionality, or you can use the proportionality between sides, either between sides of the same triangle or between sides of the different triangles. Those are different results, both very useful.